So, you might be wondering why I'm having a picture of a sandwich here. We will get to that shortly. But what I want to sort of start the discussion with is, going back through what we did during the past, few weeks, like since we started learning about machine learning and all that. We all agreed, let me just put this sandwich away, which is making me hungry as well. Okay. So, so far what we learned was that all of these machine learning models, especially the regression ones that we were trying, we were working with certain features. In this case, we are putting feature A, feature B, feature C, and then getting a yes or no, for example, or some value for a target Y. Okay? So that's what we did, for example, last week, or in the example that I actually posted for you for support vectors. We did this with linear regression and, like k-nearest neighbor regression, any sort of regression or classification model that you use, you ultimately are inputting some features, hoping that your machine learning model would find the method by which it would sort of come out with predicting your Y variable, that you're interested in. So we are all clear on that, and I hope that you are. If not, you need to watch the previous videos. But there is one factor. Imagine when we were kids, and your mom or your dad would tell you, for example, don't do this. Okay, for example, don't put your hand into the electric socket. And you could either, as a child, just obey and say, okay, Dad said don't put your finger in the electric socket, so I'm not going to do that. But then as you grow older, I'm sure that many of you, including myself, would then ask your parents, why not? Yeah, that question of why not? Why shouldn't I do this? Why shouldn't I put my finger in the electric socket? And at that point, your parent would start telling you about, well, there is this thing called electricity, and if you touch it, it's going to shock you, and it could be harmful or fatal, basically. And as such, you got an explanation for what was correctly being told to you. Okay? So when we run these machine learning models, okay, and assuming that we run a machine learning model that is working fantastically well, okay, so we are inputting feature A, feature B, feature C, and it's precisely, perfectly is predicting the target Y, okay. Well, one question. Okay, we know the model is working well, but then why? I mean, which feature is having an importance here? Is it feature A? Is it feature B? Do we even need feature C? Because in the black box of your machine learning model, you technically don't get that, do you? You just run the model, you train it, then you do evaluation. It's either doing really good or it's doing really crap. Yeah, so it's either of these. And assuming that your model is perfectly working okay, you can be satisfied with saying that, yeah, that was a good model. Thank you very much. Amazing, and leave it to that. But I'm sure that many of us would then wonder, okay, which one of these features is important in this model? Fair enough, my model is working good and it's really great, but I'd like to know what feature was important here. And that's when the idea of explainable AI, starts to pop in with all of this stuff. That fine, the models are working good, but we want to know which feature is working. I mean, like, how is this working? Initially, the idea of there was, model was proposed, which is called feature importance algorithm, or like they call it, it relies on random shuffling, basically, which I will explain that in a bit. And that was the idea originally proposed to sort of try to find out that once you have trained your model and your model is perfectly working fine, then on the next step, remember what I just said, you pay attention to what I just said. Once you have trained your model and it's perfectly working really good. I didn't say before you train your model or if your model is rubbish. You have trained your model is really great, it's predicting the Y perfectly, and now you want to know, okay, yeah, which one of these features are important? What's happening? So originally, the idea of feature importance algorithm came, I think it was pre-2010ish sort of, and it relied on random shuffling of the feature columns, or referred to as permutation. Yeah. So I have an example here so you can see with this super simple sort of data. Let's just imagine this is our data, and we have trained our model. It's amazing. It's the most glorified machine learning model ever. Yeah. But obviously we don't know what is what. You know, we want to find out which feature is important. So take a look at this image. Yeah. So we got feature A, feature B, feature C, and we have the target basically output. Okay. How would we, guys? Can you please turn off your microphone? Yeah. How do we go and perform this algorithm? Take a look. So for column A, we have kept column B and column C as it is, okay? And then we come and randomly shuffle the column A. So we literally input wrong values in there, okay? We put wrong values in there. And guess what? We do this with our test data. So we trained our model on our training data. We know that it's a good model. Then we come here, we get our test data, and we shuffle column A. While we shuffle it, we then try to see, okay, how did the model perform? Think about it. If column A is important, okay, if column A is important, and you shuffle the values, and then you try to get this data, you give this data to your model, if it still predicts really good, well, what does it tell you? That feature A was not really important to start with, because when you shuffled it, the model is still perfectly, performed great. Yeah, okay. Then you go and you do the same thing with feature B. So you keep feature A as it is, original, and you shuffle, or you permute, if you like to call it, machine learning lingo. So you permute the values of column B, feature B, and then you test again. You test your model, and you try to see, okay, is it still working good, or is the model is now predicting total rubbish? Okay, that's the main idea behind the feature importance algorithm. Okay. But as you can imagine, there is a drawback to this, yeah? And that is where I'd like to take you to that original picture that I had here. So for a second, let's put machine learning algorithms aside and let's look at this case, okay? So that I want the idea to sink in before I go to the more modern algorithm, okay? That has replaced, so not replaced, but sort of is beating or is more advanced than the usual feature importance algorithm. So we have a sandwich here, okay? This sandwich, we got a bread slice, we got some beef slice, we got cheese slice, we got tomatoes, and we got lettuce, okay? And I know there is a sauce in there, but I haven't put the sauce here, so just forget about it. Just assume there is no sauce. Okay, so let's assume that these are our input features. Yeah, so think of this as our columns. Okay, but remember, all analogies fall at some point. Yeah, but I'm trying to use this example so that you appreciate and understand the next topic when I open it up so you don't get confused. Okay, so we got bread, we got beef, we got cheese, we got tomato, and we got lettuce. If we put beef, cheese, tomato, and lettuce sandwich between two bread slices, we have a sandwich. Okay, so let's say we are trying to see if we can predict a sandwich in its globally known format. Yeah, in this case, a beef and cheese sandwich, for example. So, what does feature importance do? The usual, conventional feature importance algorithm. It would come and it would say that, okay, let me shuffle. Yeah, let me shuffle the bread. So let's replace bread with uh, crisps. Okay, how about that? We're shuffling, isn't it? Some form of food, basically. We are just going to change that. So if we replace bread with crisps and we then give the beef, cheese, tomato, and lettuce and try to sandwich them between crisps, does that make a sandwich? No. It has suddenly taken the entire meaning out of a sandwich. You basically got a slice of beef, cheese on it with tomato and lettuce with crisps under it and on top of it. Yeah, some people would like to eat that, like people have interesting habits of diets, basically. Okay. But that is not really a sandwich anymore, is it? So by shuffling the bread, we realized that it took out the entire meaning. The whole model collapsed. You're not going to get a sandwich at the end. So by shuffling the layer where you got the bread, basically, you took the entire meaning out of a sandwich. Okay, so you realize, oh, you go to yourself, ooh, bread is really important. Okay, fantastic. Now we're going through the algorithm, right? So let's go and change the beef. Now replace the beef with ham. Ah, okay, we replace the beef with ham. How is it going to look like? But guess what? You're going to get a sandwich that more or less looks the same. Okay? But is it still a beef cheese sandwich? Okay? No, it's not. But visually and in terms of texture and what you see, it is a sandwich now. So you're like, oh, so beef was not really that important, maybe. Okay? You can say that. Or you could even say that remove beef. Yeah? Let's just remove beef. You still have a cheese and salad sandwich. So the idea or the identity of a sandwich is not taken away, while if it is critical for the sandwich to be a beef sandwich, that has been undermined. But visually, when you look at it, it's a sandwich. Now, what if we go and replace the cheese? Well, still, you have a sandwich looking thing there. Okay, you won't have the cheese. So, what I'm trying to tell you is that the biggest limitation with the conventional feature importance algorithm was that while it's great to show you if a particular column is important or is not, it disregards the interaction between the features. Okay. So, I mean, I tried to use the simplest example that I could to sort of make you understand this. Yeah. So that was the biggest limitation of the feature importance algorithm. So I've written here the biggest drawback. Well, I think I've written it quite in bad English. I do apologize. So the biggest drawback thing about feature importance, permutation or tree-based importance, is that it does not handle feature interactions or correlations work. Basically, sometimes features don't work alone. You see, there could be a correlation between these features, okay? As we saw in the sandwich case, the cheese and the beef, that could be the selling point of that sandwich, like just because you only have a bread and put anything in between, it looks like a sandwich, then your model does not really look that powerful, is it? Or not your model, sorry, your interpretation of how your model is basically predicting a good sandwich is not working very well. So as such, back in 2017 to 2018, a new model was around. So this is quite modern, yeah, and it's called SHAP, yeah. So what is SHAP? SHAP in machine learning and deep learning is called Shapley additive explanation. Is a popular model that basically tries to explain why a machine learning model makes a specific prediction, and it operates differently to how the basic feature importance was basically working. Yeah. Let's say especially in the code, I'm going to be using housing data. Yeah. Let me make this larger. Okay. So for example, think of us trying to train a model that can predict a house price based on certain parameters that go in. Okay. And how would basically SHAP approach this? Yeah. The whole idea of SHAP is based on, what is known as, I don't know if you guys are familiar with the concept of game theory. Okay. So if I want to quickly give you an idea of that, okay, let's say you got a football team. Yeah. Let's say you are just watching a football team. You got 12 players. And let's say this is, I don't know, the national team of Portugal. Okay. And let's just say Ali, me, I've become an honorary member of the Portuguese football team. So I'm one of the players as well. So you are assessing the team. Yeah, they are all playing. There are 12 players. And you want to know if Portugal is now going to beat, let's say, Germany, which players, which players were most important in the game. Let's say Portugal won Germany 2-0 or something, yeah, 3-0. Okay. During this game, obviously Germans, tried to score a goal against Portugal, and here the Portuguese defense had to come to the aid, yeah, and prevent their strikes. At the same time, the Portuguese had to score goals, and obviously the strikers and the midfielders had to sort of collaborate together, and you needed one good striker to score a goal to take advantage of the opportunity. Okay. So if you think about it, you can't say, okay, just put Ronaldo in there in the Portuguese team, everybody else lay on the side, have some coffee, and Ronaldo is going to score all the goals for you. It doesn't work like that. Ronaldo is dependent on other team members to be able to score a goal, while he himself is one of the biggest assets to that team. Okay? And Ali, me, the novice of football, having become an honorary member of the team, probably standing somewhere at the back in the defense, I have the least benefit to the team. Okay? You can see that from the game. But then at the same time, it's important that who supports Ronaldo, and then how does the midfielders with the defense cooperate and try to prevent the opposing team to score a goal. Okay, so if you were to go with the original example I gave, with the original algorithm, which was feature importance, it would just come and take Ronaldo out and just would say, oh, Ronaldo important or not important, Ali important or not important. But it did not consider that Ronaldo needs to have other players in the team who support him by passing him the ball on the right time. It didn't think about that, yeah? And that's what SHAP is trying to do, okay? SHAP would try to see, okay, how did each feature, how important was each feature in terms of ensuring that the model performs well. Okay? And it's based on the concept of game theory. The game theory itself is quite an old proposal, sort of concept. I think it goes back to 1960, 57, 56. I don't know, a long time ago, yeah? Uh, but these clever guys, and I've forgotten the name, you can search it. These guys who came up with the idea of SHAP algorithm used that concept, which I tried to explain it to you through the football sort of thing, like the output of an evaluation of the sort of football play, the game theory. And they used that to try to evaluate the machine learning models and try to find out what's happening under the bonnet. Okay? So what SHAP enables us, what sort of information it would give us is that once you train your machine learning model, okay, and you know that it's working good, then it will help you, well, it will give you precise indication of how important were the features that you used during your machine learning technique. Because as such, in future, okay, if you're a scientist trying to experiment with collecting data from various other sources, or if you are I don't know, an insurance company marketing sort of person, or whoever you are, it gives you a much better indication of what features are important to collect or pay precise attention to when you're collecting these data, because your model would be so reliant on them. So it's a very, very important concept in machine learning. Yeah, the idea of it falls under the idea of explainable AI, not just run the model, do the prediction. Thank you very much. I don't care why it doesn't do. Just like the child that imagine if you become 40 years old and you still are afraid of putting your fingers into the electric socket, and someone tells you why, you're like, I don't know. My dad said so. No, And the idea of explainable AI is that why you shouldn't put your fingers into the electric socket. Okay? And that's what we're going to explore. And so obviously, this is a really big concept. And I'm introducing it to you, hoping that you will be going and playing with this. In fact, I won't be giving you the codes anymore. I won't give you any code. I hope that you will be going and typing this code as you watch the video later. Okay? So we are going to run the code. And in fact, I will be introducing. So this lecture session is going to be acting like a bonus. Yeah. While I haven't covered some other machine learning or deep learning algorithms, I will be showing you how you actually use Python to do it. Because now you have become, or you should be familiar with the idea of machine learning and how we split the data, how we make predictions, how we use pandas to structure our data. Okay. So now I would introduce models that maybe you haven't heard of before, but at least in my class you haven't heard of before, yeah? And you can then go and practice and play with. So let's think of the XGBoost algorithm, okay? It's a machine learning algorithm. It's quite powerful, yeah? And what we are going to do, we are going to import housing data database, basically, and try to first train the model on predicting the house price, evaluate the model, and then use SHAP to see which features are important. Okay, so that's what our task is today. And I'm hoping that we would finish quite early, but I really, really hope that then you go and you code along with this. All right. So to start with, we are going to import SHAP. Okay, so SHAP is the library that enables you to perform the SHAP analysis for the feature importance. You're going to import XGBoost. That's the machine learning, that's a library that would give you access to the XGBoost algorithm, a very powerful machine learning algorithm. You're going to be importing pandas, obviously, because you want to create data frames and play with data frames. And as you know, with any machine learning models, we always need to train or models on a training data and then test it on a test data. So we're going to be importing the train test split so that we would be basically able to split our data. Now, the data super simple. We are going to import it from scikit-learn's datasets, which are used for training. So from scikit-learn.datasets import fetch California housing. This is the basically data. You just need to type it exactly as that. Yeah. So from scikit-learn.datasets, import fetch California housing. And once you do that, you need to then go and say housing equals, okay, housing equals fetch California housing as a function. And last week, I've already introduced you to this. When you get this sort of data, just as a reminder, in case, so that you don't get confused. Okay, so remember, housing itself is not a data frame, yeah? It's a data pack, yeah? It's a data pack that we need to now take a stuff out of it, you know? So if I say housing, like that, you see that there is a lot of stuff in there, okay? There is plenty of informations in there, okay? And what we need to basically take out of this, yeah, out of the housing, let me just get rid of this. We're going to get the data. So housing dot data. So this is the data. Okay, these are all the data, and we can say dot shape. Let's just see how big it is. So it's we have a data set, numerical data set of 20,640 houses with 8 input features, with 8 features. Yeah, so we have 8 columns and 20,640 rows of data. Okay, and housing dot feature names. So housing dot feature names. These are the feature names. Okay, so from this housing, we are going to make a data frame and construct or data frame basically using the information embedded in housing. Okay, so and how do we do it? Obviously, let me put this separately so that I think that would be then a better sort of. So I did my housing equals fetch California housing. Then from this housing, if I do housing.feature names, it gives me this. Housing.data gives me the data. You should know by now how do you create a data frame. So x equals pandas.data frame. Okay, we give the data and we give the column names. Okay, so don't get confused over this. Housing.data was that numpy matrix basically, yeah, that array basically, right? And columns equals column names. It's just a list of columns. Okay, and y equals housing target. Let's look at the housing target as well. And that's the target. So let's look at the shape. Exactly matching the number of the rows, basically. Yeah, so this is our y. Okay, so technically speaking, if I go back up here, we got 8 columns. Okay, 8 columns, 20,640 something rows. That's our x data. And we got one y separate, basically, that we are extracting from that, you know, the housing data by housing targets. So if I run that, now I have x. So if I call x columns, I should be exactly having the same column names, you know, that were already in the housing feature names. Okay. Let's look at our data frame. So x.head gives us by default the first 5 rows of our data frame data. So let's look at it. We have medium income, house age, average number of rooms, I assume it is, average bedrooms, population. I don't know what does it mean by average bedrooms and average rooms, but anyway, population. So I guess obviously 322 people don't live in the same house. So it's probably talking about the area. Average occupancy, meaning that in each house, how many people live, basically. Uh, well, in that house is 2.5. And then latitude and longitude. Yeah. These are the coordinates, geographical coordinates of where the house is located in, uh, what was it, California. Okay. So somewhere in California, uh, based on these locations, these houses are based there. So, okay, let's become one with the data first. Let's have a quick think. Okay, so we got this data set. It gives us the medium income, okay? It gives us the house age, average rooms, average bedrooms, population of that area, how many people live in that, and then the location of the house by giving its longitude, latitude coordinate. We all know, I mean, right away, we all know that, let's say, if you live in London, obviously, if you go and, I don't know, look at the private property prices, for example, in somewhere near where I live, Hayes, okay, it's going to be cheaper. It doesn't matter how many rooms he has. It doesn't matter how many, what a big garden he has. Like for like, it will be cheaper if you compare it with the same house in High Street, Kensington, or in Chelsea. Okay? But obviously, Chelsea, High Street, Kensington, well, each of those would have their own latitude, longitudinal location. Okay? And you can't get it more precise than this. All right? So right away, we know that these two are going to be important. Yeah? They're going to be very important because in house price, that matters. And then population. Obviously, when you have a place where you have 322 people, it means it's less populated. If you got 2,401, well, that indicates a lot of apartments, I assume. Yeah. Um, so, we can sort of guess that in a sense. But then look at the longitude, latitude. These two are in the same area, aren't they? Okay. Um, That's our data. I mean, technically, we sort of know what our data is all about. Okay. And let's look at the Y train. Sorry, what was it? Oh, Y. Let's look at the Y as well. Okay. So this is probably in hundreds of thousands, I don't know, dollars or pounds or whatever. Whatever it means. Yeah. Whatever this Y means. So let's start to begin like act like data scientists. At the moment, we're going to say like, you know what? I don't care. I just want to train and see if I can predict Y from uh, this X and from this feature. Okay. So that's our data. We're going to be training our data with these inputs, trying to predict this output. Okay. So right away, we all know this. X train, X test, Y train, Y test equals train to split. X, Y, this is our Y, this is X. Go and fetch 20% and keep it as a test size, keep it on the side. And we're using a random state of 42 just to so that, if you do this at home, you're going to get the same results as me. Okay, so let's do that. Okay, we have now our X train data. Let's just quickly check that. X train dot shape, X test dot shape, Y train dot shape, and Y test dot shape. Okay, let's take a look. Everything seems good. So we have our training data, 16,500 points, and related to that, or Y train, yeah, Y train, they're matching, perfect. Or X test, 4128 rows, 8 input features, and 4128, that's our Y test. Everything is going beautiful. So now from XGBoost library, we import. This is our machine learning regression model. Okay, so please try to do this yourself at home, watching the video, coding it in. So from XGBoost, import XGB regressor. We got a model. Now we make, I don't know why I didn't forget to put the comments in. I always tell people to comment it, but I didn't do it myself. I think I was in a rush to sort of prepare it. So make an instance of the model. Okay, so we make model equals XGB regressor. Thank you very much. Our model is made. And now let's train our model on the training data. Obviously, going to take a bit of time. Okay. Bear in mind, this is a vanilla, super simple XG boost sort of regression model. Yeah. Otherwise, you can vary many different parameters in there, but we are not going to stick to that. We don't care. At the moment, I want you to learn SHAP. Yeah. So we have used the vanilla basic form of XGBoost regressor, right? And we just fitted it on our training data with our Y train. So that's the model is fitted. Okay, the model is fitted. Now look at this. Step one, evaluate the model. This is what I said right from beginning. Evaluate the model before using SHAP. You do not go and use SHAP unless you are sure that your model is amazing. If your model is totally rubbish, there is no point of doing SHAP. Yeah, there is no point in doing it. You only do SHAP if you want to evaluate a good performing model. So do not do SHAP before you have first evaluated your model. Okay, so we need to check if the model is any good. So what does this mean? This means we need to evaluate Y-pred, predicted value, against Y-test. So let's import our metrics, importing our evaluation metric. Okay, from scikit-learn.metrics, import mean absolute error and R2 score. Yeah, two of the best. Well, R2 score is my favorite, of course. This explains the variance in your sort of predictions. But to be honest with you, when you do a regression analysis, R2 score is the one. Okay, that tells you how good your model is. But mean absolute error, of course, it gives you an indication of how your model is performing. So let's go step by step. So I'm importing the relevant metrics that I need. So I've imported the metrics. And then I'm going to now make a prediction. Okay. So I'll put all of these in the same cell, but obviously, you can put them in separate cells. Yeah. So YPRED equals or model that was trained. So it's equal trained model. Okay. So YPRED equals model that predict X test. Okay. And right away, maybe it's better. All right. So YPRED equals model that predict. So let's do that. That's it. We have our YPREDs now. So YPREDs. There we go. What will do? Sorry. That's our predicted values. All right. Again, we want to check, we want to go with SHAP, yeah, and find out if features are important. But we first need to know now. Go and see if your model did any good by comparing this to your test data. Okay, cool. And how do we do that? We use our evaluation metrics. MAE equals mean absolute error that we imported, Y-test, Y-pred. So we are saying mean absolute error function. Here is my Y-test. Here is my Y-pred. Go and find out what is the mean absolute error. And R2 score, we are saying R2 score. Go and fetch here is my Y-test. Here is my Y-pred. Give me the R2 score value. And then here, print using a f-string print statement with certain sort of decimal places to give me the mean absolute error on the R2 score. Let's do that, and we see, mean absolute error is 0.31, but as I said, this is the one you're after. The closer this is to 1, the closer this is to 1, the better. And at 0.5, your model is junk. Why at 0.5 is junk? Because it just means your model is guessing, it's tossing a coin. Okay? So really, a R2 score, a good R2 score, let me just put it here. Good R2 score, literally you're looking at above, bigger than sort of 65%, in my opinion. You know? Once you're beating above 65, then it means, okay, your model is doing something. But guess what? Oh, and one thing, guys, if you ever get an R2 score of 1, be sure that something's gone wrong. I mean, that only happens if God comes and kisses you or something, yeah? Usually, I mean, you might even get a 9, you might get a 0.99 even. And if you have really worked on your model, if you have done thoroughly fantastic data pre-processing, and there is a relationship that your model can learn. So you might even get on some occasions 0.99, like in rare cases, yeah. But if you ever get a R2 score of 1, definitely know there is something wrong because nobody gets that lucky. Okay. Anyway, so because we got a 0.83, that sounds really good. 0.83 means it's good. Okay. Excellent. So now that it is good, we can basically go and do it. But what if it was 0.5? Do you go and do SHAP? No. You first go back and try to see if you can improve your models by altering the input parameters of the hyperparameters of the model, by trying to sort of see if there is any errors or anything wrong with your data. Uh, adjusting, for example, if you're doing deep learning, like adjusting the learning rate. If you're doing, I don't know, random forest, changing the number of trees or blah, 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 blah. You basically try your best first to get a very good R2 score, to get a very good model, okay? And only then you go toward analyzing, your performance with SHAP to find which features are doing what, okay? So now that we are 0.83 and that is really good, we can go and learn how to do SHAP, yeah? So you remember, we already imported SHAP, yeah? Let me just write it. Why did I go there? Remember, we already imported SHAP, yeah? Okay, so I've already imported up there, but usually I try to import it at the point here. I did it earlier. Anyway, so what we do, I mean, obviously you can call this Mickey Mouse if you like, but explainer would be a better point. So we're going to say explainer equals SHAP dot explainer dot model. Remember, this has to be the trained model. Okay? Don't just go and make a model without training it or anything. Come and then feed it into the SHAP dot explainer. This is your trained model. Yeah? Trained on training data. So you come and say explainer equals SHAP dot explainer with capital E, and you feed your model into it. Once you do that, you got the explainer. Okay? Now you need to extract. Now extract the SHAP values. SHAP values are the values that would indicate how each feature is important. Okay, so that's what it says. That's what SHAP values are. As we were like, how important was Ronaldo? How important was Ali? Okay, so that's what SHAP values are. So extract the SHAP values. So SHAP values equals explainer. And look at that, guys. Look at that. Note, we are giving it or X test, not X train. Okay, not XCX. Okay, so SHAP values equals explainer X test. Understood that? It's going to take some time. And I want you to think about it. Why did it take some time? Okay, well, it takes time because it goes and, like, just think of that. With the SHAP, it tries to imagine on a piece of paper, you yourself. Technically, what SHAP is doing, what the SHAP algorithm is doing, is like as if on a piece of paper, once he has trained the model. Let me go back up and explain this quickly. So what SHAP is doing, yeah, it's going through the model with your X test data, and it looks at first row. Then it comes and says, 5. Let me increase it to 6 and see what do I get for the target. Imagine you're doing this by hand. Yeah, imagine you are doing this by hand, one by one, for every single feature in every row. Okay, that's what SHAP is doing. So then it goes to 7, it goes to 8, it goes to 9, and records what Y comes out. Then it increases, does the same thing with B, then does the same thing with C. Then does a combination of two features together. Okay? And then does a combination of C and A, and then B and C. Okay? And that's how powerful it is. While the other method just shuffled one of the columns. That's it. Whereas SHAP takes every single row and keeps varying this value in feature A, monitoring the target, seeing if it goes up or down. Then does the same with this first row in B, first row in C, and then a combination, altering them by combination, then going to the next row. So it's compared to the first algorithm, the basic algorithm, it's extremely computationally expensive, yeah, but it's great. So I hope you understood what SHAP is doing technique. So you could literally do SHAP on a piece of paper on your hand, but you probably would take maybe, I don't know, 4 or 5 years just for this basic data we were looking at until you complete it by hand. Okay, so let's go back and all right. Okay, we did this. SHAP values equals, so now we have the SHAP values. Okay, so did I run this? Yes. Oh yeah. And let me write this here as well. Pay attention to the time it takes. Okay. So now let's look at SHAP values. Okay. So that's it. These are our values basically that has gone and sort of extracted. All right. So you can go and explore further about this. Yeah, I'll leave it to you. Okay, once you become familiar with the idea. But for the moment, just think of SHAP values as the importance. Okay. Now, to plot this, obviously we want to visualize it. We are now eager to see, oh, okay, great, Ali, let's see which of these features were important in this case. So you use the function sharp.summaryPlot. Remember, we are not using pyplot. So we are not using matplotlib or anything. We are just calling the visualization, right? Let me just write it. We get the visualization tool directly from SHAP itself. Okay. So what do we do? Oh, didn't want to do that. So sharp.summaryPlot, SHAP values, which we already picked out here, these values, and we are saying plot it against our X test. Okay, that's what we're doing with our X test. So let's see. And then it comes up with something like this. Okay, and the important bit now is what I want you to sort of see is how do you interpret this? Okay, well, amazing. What does this mean? Okay, so let's look at the y-axis. SHAP values, impact on model output. Okay, so looking at this, 0 means no effect. Yeah, so 0 would mean that this feature did nothing, had no effect. Okay, 2 means wow, extremely positively affected the output, whatever the output is going to be, whether it's a house price or whether it's any other feature about the house. 2 plus means it's highly affecting it. Minus 2 means it's negatively affecting it. Okay? Negatively affecting it. And let's now look at the features. We got latitude, longitude, medium income, average occupancy. Have you noticed something, guys? Yeah? If I come and say, let me just put it here. So if I said x dot columns, look at the order of our data. It was met, house age, average rooms, and these two were actually at the end. But look at that now. They are ordered according to their importance. Okay? So they are ordered according to their importance to the model. So latitude, longitude, this means they are highly important in the outcome. Minimum income, average occupancy, average rooms, house age, population, average bedrooms. Okay? Now you can imagine, I mean, sometimes you need to understand your own logic. For example, have you noticed, guys, in the UK, the house age doesn't really affect the price of a house that much. Obviously, if it's a new house, people like a new house. It's a bit more expensive, but not by that margin. But if you go to somewhere like Turkey, where there is a possibility of earthquakes, you can imagine house age is going to, I mean, like you have gone, I'm sure all of you have gone to UK, you go around in countryside, you see 300-400 years old pubs, you know, like really vintage pubs that you're going to have a beer or something. And what usually if you go to Middle East, you don't happen to go in a house, you know, like a common pub or house or something that is 400 years old because they always have earthquakes and those sort of buildings don't survive. Okay, so house age and the considering that these sort of regulations affect how many safety features they need to implement in building a house. So something like house age would be important for that market. So have an open eye on these things. Just because this model performed well on California, for example, it does not mean that it would be like the same in Turkey or I don't know, in Germany or whatever. Anyway, okay, happy doopy. So what does this all mean now? Okay, what does these red dots and blue dots basically mean? So they indicate that low feature value, listen carefully, low feature value, let's look at the latitude, yeah? So low latitude values, we are looking at only latitude, yeah, so that you understand it. And I'd like you to go and explore this yourself later and try to learn interpreting this, yeah, interpretation of this. So if you look at latitude, if latitude goes lower, it tends to have a positive effect on it will tend to have positive effect on the output, on the Y. And if latitude goes high, the value of latitude, it will have a significant negative impact. Okay? That's what this means. What does it mean if they are really broad? It means that, well, it's very broadly distributed. Okay? Like, it just clarifies the very high importance of latitude, basically, technically speaking. But then you come and look at something like average bedrooms. And with average bedrooms or like this population, you see that these red dots and blue dots are completely mixed with each other. And not only that they are really mixed with each other, they are not, they don't seem to be that impactful. Okay? So you got like -5 and you got 5. Okay. Hmm. That just clearly indicates, first of all, the fact that it's at the bottom of the list means that SHAP has already found out that they are least important. Not important at all? No, I wouldn't say that because you can see some resemblance, but very weak. Okay? So definitely your top players are to some extent house age, average rooms, okay? Average occupancy, and of course latitude, longitude. And latitude and longitude significantly affect the outcome positively or negatively because they are very broad. Whereas here, when you've got a blob of this thing happening here, it means that, okay, once they are low at a certain level, it doesn't matter how low, how much further low it can go. At a threshold, it will be just having a negative impact. That's what this means. Okay? What time is it now? Because I really have to finish at 1:15. Okay. So that's that. And as I said, I'd like you to go and try to code this out. And finally, we said that the whole point of SHAP is, we said that the previous models sort of gave you this in a sense to some extent, yeah, by randomly shuffling a particular column and telling you about its importance. But we said that SHAP gives you the ability to also see which features are correlated and actually work in synchronization to make, to impact the outcome. To do that, you use this method. So we said SHAP, let me just say, SHAP summary plot, meaning basic plot. So the summary plot of SHAP just gives you this, a good indication. Straight away, latitude, longitude are important, very important. The third one, fourth one, quite important. It gives you a snapshot of the whole thing. But then you can go with SHAP.dependence plot. Okay? So much more detail as well as clarifying interaction between features. Okay? So SHAP.dependence plot would give you that. So what do we give to this dependence plot? Look at that. We put name of one of the features. Okay, so you need to learn this pattern. So to do the dependence plot, okay, you give one of the features in, okay. Then you use the SHAP values.values. What is SHAP values.values? Let's see. Okay, so SHAP values. Now let's quickly say type. SHAP explanation. Okay, so it's not a NumPy type data. What if I say SHAP.values.values? NumPy array. So what does this tell you? That you need to give the SHAP values in the form of NumPy array. So give important, let's say. Give the SHAP values as NumPy arrays. Okay? And of course, you give your X test. Yeah, you have to give the X test. And then interaction index. Yeah, you want to know meta-inc is interacting with what? So you give your house age, for example. So if you do that, yeah, then you get something like this. Okay. And again, here you have the first feature that you gave to it, and it's looking at the house age. Okay. And it's trying to tell you, firstly, the shape of this if we can see that it looks like as if it's a straight line sort of, yeah. So this seems to be, there is some form of maybe correlation to some extent in this, and also tells you how does this get affected by the house age, okay, by how these plots are made. Really, to be honest, interpretation of this, I really need to leave it out to you, okay. Now that you know what it is, I'd like you to go to Google and say, I want to know how to interpret these results, yeah? And I want you to practice and learn them on your own, because knowing how to interpret these takes time and you need to invest it yourself. But what I do is that I'll leave this for you, okay, before I close the lecture, so that at the end you can go and copy this exactly. Let me just increase this. For example, I have used house age, average rooms. What I have done is that I've put these hash marks here. So what you can do is then write this the same way and then activate each, run it, and see what sort of interaction do you get between the two features. Yeah. So like if I run that, okay, what does this mean? You know, how does this? What would this indicate to you? I really like you guys to go and invest time and learn this on your own. It's very important, yeah, especially if you want to become sort of a machine learning guy, you know, and or if you're a MSc or a PhD student and you're doing your experiments, like you're doing chemistry experiments or something, and you want to know, okay, these inputs that are put in this sort of tests, and I've found out the importance of which is important, what is their interaction with each other, you definitely need to do this. Okay, I hope you have enjoyed this. I've prepared some other stuff that probably maybe I would try to cover next week. Before I go, I just need to tell you this. So for different machine learning models, okay, it's not like I've actually written it here. Can SHAP, why did I put shape, sorry. Can SHAP be used with any model? Well, sort of. You need to be careful. How? If you're using k-nearest neighbor, you need to use a kernel explainer. Okay? If you're using random forest, you need to use the tree explainer. If you're using support vector machines, then you use that. Okay? Now, you can go and do this with the same data. So if you have coded, if you watch my video and you're coding up to this point, I will leave this here so you can pause the video and you can read it. Then you can go and run these on your own. Okay, so type them in. This is for a k-nearest neighbor. Okay, and how you would use a different kernel. In fact, when I did k-nearest neighbor, it was absolute rubbish. Yeah, it didn't perform very well. But you know, try it. But take a look at how you do the SHAP. Yeah, you see, I do the SHAP kernel explainer. It's a bit different from when I use the XGBoost, okay? So be aware of this, and if you want to do random forest, again, you watch this video later, you pause it, you code it, okay? And this is how you do the SHAP. You do SHAP.tree explainer. And SVR, which we did last week, again, this is a support vector regression model, a very basic one I've put here. Pause the video, code it out, and then once you coded it out, use the SHAP like that. And obviously I have deep learning, I've prepared this, but I'll get to this when I follow in future weeks when I teach you deep learning, okay? All right, guys, I hope you have enjoyed it. I need to shoot off now as well. So, yeah.